Hello dear students, welcome to THATSIIT YouTube channel. I am KASU sir discussing the JEE advanced level concepts through the previous year questions, and we had already seen the last two sessions wherein we had covered the most important stoichiometry as well as the atomic structure kind of chapters, and you have seen the importance of those topics as well. And in particular, when it comes to the stoichiometry, the question seems to be a little bit complex, but the question part is complex, but when you solve it, the solution becomes easy once if you get the abstract idea, that means how to solve the questions. So remember that JEE questions are difficult to understand but easy to solve. So remember this quote. It's not that it's just a quote, it's a practical observation that when you first look at the JEE advanced question, you might fumble a bit. The question language, the question complexity levels appear to be a little bit difficult. But once if you understand the concept involved in it, I'm telling you, you won't require even 2 minutes to solve it. Alright, so might seems to be an exaggeration, but it is truth. So we need to understand this, we need to adopt this, that the JEE questions are difficult to understand but easy to solve. With the same motto, let's move ahead in our sessions or discussion. Today we are in the thermodynamics, thermochemistry and equilibrium related questions. As you know that this is regarded as one of the complicated topics from which the lengthy or tough questions might be asked in JEE advanced as well. The experience of the students who had written the JEE last year say so that the questions which were asked from these chapters, in particular thermodynamics and all, were little bit complex to think. The questions won't be as straight as they were asked in JEE main or other entrances. As you all know that in JEE main and other entrances, the questions that are asked are usually NCERT based. But when it comes to the advanced, the application could go to any extent. But the core or the concepts remains NCERT only. That means if you are fundamentally thorough, conceptually thorough, you won't require much time to solve these questions. Alright, so let's move on. Thermodynamics, thermochemistry and equilibrium, your 11th portion, isn't it? Now let's see the first question, which is actually from the ionic equilibrium. Alright, question looks to be little bit complicated, but when you try to get into the depth of it, you will easily understand. You can see that there is a solution actually of PbSO4 which is studied simultaneously in two solutions. So normal PbSO4 is given and solubility is asked, where you will say solubility equal to under root of Ksp is JEE main question or NEET question. But when they mix up some other solutions and try to make the concept trickier, that's JEE advanced. But the mixing won't make things complicated. Let's see how. You can see you got Na2SO4. This has multiple components in the solution. I am taking the first component, that is Na2SO4, and taking the H2SO4 dissociation also into consideration. You can see that in the question that the Ka1 is very large. That means there are two dissociations related to the H2SO4, as we all know. Alright, this is first dissociation, and HSO4 minus dissociating is second dissociation, isn't it? Now here lies the important part of this question, that the first dissociation is very high. That means you know that Na2SO4 is anyways a soluble salt. Therefore, whatever concentration of the salt that we have it over here, that is 1.8 into 10 power minus 2, would be the concentration of the sulfate ion which are obtained from this, because you know that it is completely undergoing dissociation, totally forward, because this is a soluble salt, isn't it? But when it comes to H2SO4, you have taken indeed how much? 1 molar. And you have to anticipate that the whole 1 molar is getting dissociated to give you 1 and 1 molar of these two ions, because it is said that the Ka1, that is first dissociation constant, we call it as Ka1 and Ka2, isn't it, is very high. That indicates that this is going very much in the forward direction. That means I have assumed here that the H plus as well as HSO4 minus which are formed is almost dissociated, so you will be getting maximum amounts. Alright, now from this HSO4 minus, you can see some amount is getting dissociated. Let's say some X is dissociated in the subsequent equation. Alright, so you can see overall this is present in the aqueous solution of PbSO4. So actual solution is what? This one, isn't it? Now we are solving the question to find out the concentration of what? You can see the question, right? The question clearly says that the solubility of PbSO4, that is concentration of this sulfate ion or whatever, is actually X into 10 power minus y. You need to find the values of X and as Y. To get into that, let's see that there is a common ion effect, isn't it? Because you know that this and this are strong electrolytes, isn't it? Because you can see that they are dissociating almost completely. So presence of, what do you say here? Presence of Na2SO4 and H2SO4 decreases the solubility of PbSO4, isn't it? Okay, so after such decrease, after pushing this equilibrium in the backward direction because of the increase in the concentration of the sulfate ion by the production of the sulfate from these two substances, let's assume that the solubility, that the concentration of Pb plus 2 which is formed is some S. Now you can see there is 1.8 into 10 power minus 2 mole of sulfate ion which is indeed present over there. Alright, and X amount of the sulfate ion which is present out of the HSO4 minus dissociation. You can see that the dissociation part is smaller in comparison to this value, because you know that this is stronger. So we can say that the concentration of the sulfate ion indeed, actually when you take it into account, how much is that? 1.8 into 10 power minus 2 plus sulfate ion which is obtained from HSO4 minus also, but I will ignore this. Why am I doing this? Because you know that Na2SO4 is going to oppress or suppress the dissociation of HSO4 minus also, because Na2SO4 is a stronger electrolyte compared to this, because its dissociation is lesser. Anyways, it is suppressing this. There is no doubt about it that the solubility is decreased, but the dissociation of HSO4 minus is also decreased. So Na2SO4 is not only suppressing PbSO4 but also suppressing HSO4 minus. So because of this, what will happen? Some equilibrium, the equilibrium would be shifted in the backward direction, isn't it? Let's assume that it has shifted in the backward direction. That means I will take the total concentration of the sulfate ion here is somewhat 1.8 into 10 power minus 2 only. Have you understood this particular step? Alright, minus some A moles of the sulfate ion has reacted in the backward direction, and you can see that the H plus ion concentration, the X value is very much negligible compared to the H plus which is obtained in the first step, because the first dissociation is very large. Therefore, I will take the concentration of H plus as 1 only. So since this has shifted in the backward direction, the number of moles, that means X is small, the number of moles of HSO4 minus is actually produced how much? 1 plus A. Therefore, I will take the second dissociation of the H2SO4, that is Ka2, whose value is 1.2 into 10 power minus 2 is equal to concentration of H plus into concentration of SO4 minus 2, that is 1.8 into 10 power minus 2 minus A. Hope you understood. Therefore, A value is turning out to be, you can see 1.8 into 10 power minus 2, this is 1.2, that is 0.6 into 10 power minus 2. Alright, so concentration of sulfate ion we got equal to 1.8 into 10 power minus 2 minus A. Alright. Therefore, as you all know, the KSP of PbSO4, which is equal to how much is given? 1.6 into 10 power minus 8 is equal to concentration of Pba plus 2, that is S, into 1.8 into 10 power minus 2 minus A, that is 0.6 into 10 power minus 2, that is 1.2 into 10 power minus 2. So you have to get the value of S from this expression. Hope you understood. So you have to make certain approximations if you want to solve the question from ionic equilibrium. What are the approximations that I made? I took the concentration of H plus totally as how much? 1. I did not consider the dissociation backwards, that means the value of X. I have ignored the value of X, that is nothing but the sulfate ion which are obtained from this. I took the sulfate ion as if it is coming only from the Na2SO4, but because of the backward shift by the addition of Na2SO4, some moles of SO4 minus 2 have also reacted. How many moles? A, and that will add to the HSO4 minus in the backward direction. Alright, so you got Ka2, and from Ka2 we got the value of A, and from that we got the concentration of sulfate ion, and we have substituted there to get the right answer, isn't it? Easier. Alright. So let's see, the equation looks to be mathematical, looks to be sound, looks to be a connection between the equilibrium as well as the thermodynamics, but not complicated as well, right? You know, the question looks to be complicated, but when you understand, I'm telling you repeatedly, it's going to be very easy. You can see there is a reversible reaction which is taking place, for which the plot of Pz by P0 versus 10 power 4 by T is given as a straight line. And the expression is also given, isn't it? So here the expression will help you in solving this question, equal to minus delta H naught by R into d of 1 by T. Now if you want to get this expression into picture, where you can see the equilibrium constant might be given as the ratio of Pz by P0, that is nothing but the K. Now you see, whenever you get this equation and you want to end up at delta H naught or delta S naught, you have to take into account the integration, isn't it? As you know, this part gets cancelled. So what is that overall equation that you get? Natural logarithm of K equal to minus delta H naught by R into 1 by T, and there should be a constant whose value is, like we learned in thermodynamics through the Gibbs-Duhem equation, that it is nothing but the delta S naught by R. That is the value of the constant which you get when you do the integration of this equation. Now you can correlate the data. Now we can see or correlate the graph and check out, right? Y equal to minus mx plus c. You can see it has got a positive intercept but a negative slope. Alright, you can see that you need to find out these concerned values. So you have entered into a form wherein you can get the values of delta H naught as well as delta S naught. Look at it now. Now we can see the slope, right? Now how do you find out if you want to solve this question? You know that slope we write as what? Dy by dx. So that is 7 minus 3, 4 by dx is 12 minus 10, that is 2. But it is negative slope, hence we write this value as minus 2, isn't it? Now we can see from this expression y equal to mx plus c, you can see the slope value is equal to what? Delta H naught by R equal to 2. So the value of delta H we got 2 into 8.314 joules. So first question is done, isn't it? Now when first question is done, obviously you have done the second question as well, right? You know, you can see that over here the ratio of these two, when you are going to substitute, alright, you are going to get the other values also. Okay, so how much is that? You have to find out the delta S naught when the temperature is, I am going to substitute the values over here, right? Natural logarithm of K is equal to, alright, delta H naught by R, that is nothing but the slope, which is equal to minus 2 into, as the values are given, you can see 10 power 4 by T. So into 10 power 4 by T. What is the temperature over here? 1000 plus delta S naught by R. Alright, so you got here natural logarithm of K equal to minus 20 plus delta S naught by R. So delta S naught equal to natural logarithm of K plus 20 into 8.314. So this is the answer for the second question. Hope you understood. Any confusion? Alright, now what you need to do is that you need to substitute the natural logarithm of k at any point of time, isn't it? Natural logarithm of k, that is that nothing but natural logarithm of this thing. You can substitute, right? You can see that the values are given upfront, so you can substitute any value. You can substitute -3, you can substitute whatever, I'll substitute -3 and solve the question. That's it. Hope you're understanding, right? You can substitute any value, doesn't make any difference, right? Now look at the next question. Again seems to be you can see when the chapters are around 40 in chemistry, and when questions need to be asked around 18 to 20, which happens in JEE Advanced, they will always fuse. That means two concepts are combined together to give the question. The favorite and deadly combination is nothing but thermodynamics and equilibrium. And you know that there is a proper connect between the second law of thermodynamics with equilibrium. So they might link up these two and ask the questions like you can say Gibbs free energy. The first law related or thermochemistry Hess law related or Kirchhoff equation related questions are mostly asked in JEE main, but second law related, entropy related, Gibbs free energy related and correlated with the what you call equilibrium constant or linked up with the electrochemistry E0 value is a very important way of asking the questions, wherein 3-4 chapters can be fused together and can be asked. So there is a chance of clubbing what you call the gaseous state with stoichiometry, gaseous state with atomic structure with stoichiometry, periodic properties with chemical bonding, and all this fusion will take place to cover maximum chapters, right, for JEE, because question need to be asked are around 18 only. So they will mix up. So that's the reason why we are mixing up and studying, so that you can understand the fusion, right? You can see this is the partial pressure of B at a particular temperature, alright, and with time you can see at 2 instances the partial pressure of B remained constant, right? One remained constant at a certain time as 10 and remained constant at 100. That means these are the equilibrium situation. You know that at equilibrium the composition of the reaction mixture remains constant, isn't it? Hope you understood this point. Alright, so we use this expression, right? Delta G naught equal to minus RT ln K. So delta G1 naught is equal to minus RT natural logarithm of Kp1 and delta G2 naught equal to minus RT natural logarithm of Kp2. All this is like 1000. There are two equilibrium. The equilibrium is changing with temperature, because you know that it will shift the equilibrium. The temperature causes the equilibrium to shift, and also the equilibrium constant gets affected. So you can see at two temperatures these values, 1000, the reaction at 1000 Kelvin at the time T dash, you can see the temperature of the system was increased to 2000 and equilibrium has been attained, isn't it? Now you can see that this you have been asked to find out the ratio, right? So this is heated, so this is at 1000 Kelvin and heated to reach the equilibrium back at 2000 Kelvin, isn't it? So you need to substitute the values T1 and T2. You have to find the ratio, so it is upfront, right? Delta G1 naught by delta G2 naught, the ratio is asked, R get cancelled, alright, minus anyways got cancelled. 1000 is the initial condition where it is log of how much? G1 naught by G2 naught or G2? So log of 10 divided by 2000 into log of, at this point of time it is given as how much? 100, isn't it? So you can find out the ratio directly, alright. So it initially the equilibrium was at 1000 Kelvin and later on increased to 2000 Kelvin and two equilibrium constant, that means two partial pressures of B can be obtained. You have been given the partial pressure of the B only. I think this way you can get the answer to the question. I hope I made no mistake, isn't it? So some students are wondering, so why are we not considering the pressure of A? You can see that it is maintained at 1 bar only. That means throughout the process the partial pressure of A remained as 1 bar, because when you are writing the equilibrium constant, that should also include the A, but this is remaining as 1 only. So it is solely dependent on the value of only this thing, isn't it? Have you understood? Okay, so just take the ratio, get your answers. Alright, temperature is increased, partial pressure of, because when it is increased, the equilibrium is shifting in the forward direction and pressure of that of B has increased, right? That's it. So let's see the next question. Looks to be little bit theoretical. The pressure work is given, right? That PdV. Alright, so you can see that this is nothing but the work done which is mentioned, and you see for van der Waal real gas equation, what do you get? P plus per mole of the gas into V minus B equal to RT, or P is equal to RT by V minus B, alright, minus A by V square. So what you can do is you can substitute over here and you can rewrite the equation, right? Minus P, instead of P you can write the whole value, isn't it? Into dV. So this seems to be the equation for real gas. The process is reversible and isothermal. For any process, the work done due to the displacement, expansion, compression, expansion, we take it as negative in chemistry. So this is called force into displacement or pressure volume work, right? So whether you take adiabatic or isothermal, only the equation would change when you want to find out what you call the work done for adiabatic. You will write it as minus NAV dt for expansion. This is adiabatic. For isothermal, it will be minus nRT, natural logarithm of V2 by V1. Okay, but before that, this is the work done for any gas, right? And this is for reversible as well, right? The process is irreversible at a constant pressure is a wrong answer, right? This equation is pertaining to what? Reversible expansion if it is negative, right? So the right answer for this question is A, B and C, right? Let's see one more interesting question. 1 mole of an ideal gas is at 900 Kelvin, undergoes 2 reversible process. You need to identify. This type of graph related questions are very much asked in the JEE, especially in advanced. You need to identify what process is that. Once if you identify, you are done. I mean to say, you can see that there are 2 processes, 1 and 2, and it is given that the work done by the gas in 2 processes is same. Alright, so I will assume that the work done here is W1 and W2. That means it is given the condition is W1 equal to W2. This will help you in solving the question. But you need to identify what process is it. You can see here in the first process, as you could see that entropy is remaining constant. And is nothing but Q by T. You know that formula for entropy. So S is constant, that means Q is also constant, that means it is adiabatic. Alright, so for adiabatic you know how to find out. W1 equal to minus NCV delta T, isn't it? How do you find out what you call the work done? Work done equal to, right, adiabatic Q equal to 0. So alright, W equal to delta U, but you don't require because you are given directly this delta, I mean U by R is given, so you can find out, right? So you don't require this, is nothing but delta U. Alright, you can directly write the value over here. It is U by R is given, right? So delta U for this process is, okay, is 2250 minus 450 into R. This is the value of delta, because U by R is given, that is how much is this? 1800 R. So this is work done, whether that is expansion or compression. I just ignored the minus over here, I just took the difference. So that is 1. If you take minus also, you will get the same value, right? Minus 450 plus 2250 is nothing but 1800 R. When it comes to the second process, you can see that in second process, U is constant. As you can see that U is constant. In second process, U is constant. U is constant means temperature is constant. That means this process is isothermal. For isothermal, you know how to find out. Alright. How to find out work? Minus nRT, natural logarithm of V final by V initial, V3 by V2. Okay. Alright. So I'll ignore this negative positive component because I need to equate it. I have to use this condition, isn't it? Alright, but I need to find out this temperature. For that, I'll take the help of this equation. At this particular case, U equal to NCVT. So you can see that it is 450, N is 1, into CV is being mentioned as how much? 5 by 2 R, isn't it? The CV value, how much is given? 5 by 2 R into temperature. Alright. So you got the value of the temperature as 450 R by 5. So you're going to substitute here R into, alright, temperature is how much? 450 R by 5, natural logarithm of V3 by V2. Now I am going to apply this condition wherein you will equate 1800 R is equal to R into 450 R by 5 into natural logarithm of V3 by V2. Alright. So you have to find the value of V3 by V2. Looks to be complicated. The only point is you need to identify the process. I hope you identify the process and all the question, isn't it? So let's see the next one. Beautiful question. It's all about the working fuel cell. You should know how does the fuel cell work. You can see that this overall reaction is by nature is exothermic, and you can see entropy is also increased. Therefore, this can be made functional. This is negative means this whole thing will become positive. This can be made functional by taking the lower temperature. So fuel cell works usually at lower temperature or medium temperature. You cannot take high temperature. If you take high temperature, you can see this delta G will become positive. However, what are the reactions that are taking place? You just know what's happening here, that your H plus is getting, alright, O2 gets reduced, alright. So let's write the equation. I'll write pertaining to half mole only. Okay. And then I'll write this equation, H2 giving rise to 2H plus 2 electrons. Now when I'm adding up these two, you can see that electron got cancelled, and this is the net equation that is given over here, isn't it? Half O2 giving rise to H2O. Isn't it? Your H plus got cancelled as well. Alright. Therefore, you can see for this overall process, this entire process, you have to convert everything into what? Delta G naught, because in fuel cell, the maximum electrical work that is obtained from an equilibrium situation, W equal to delta G naught. Remember this. The work done is delta G naught, and delta G naught is how much? Minus N. N is not 4. You should not take this because this is per mole of oxygen. You have taken only half mole. So N equal to how much? 2 into F into 1.23. So this is the work done, isn't it? Which is equal to NR delta T by gamma minus 1. Because you can see that it is related to the monoatomic ideal gas in a container. So this whole thing is used to, this energy is used to expand, alright, or compress 1 mole of a monoatomic ideal gas. So the whole energy, the whole work which is produced out of the fuel cell is used to compress the monoatomic ideal gas. So that work is converted into the compression work, right? So this efficiency is however only 70%, right? We forgot to take that. So N of that particular gas is taken as how much? How many moles of the ideal gas? 1 into 8.314 into temperature change you need to find out, and monoatomic gas is the gamma value is 5/3 minus 1 is equal to this whole value. Alright. So from here you need to find the value of delta T. So this question has got nothing to do with the other information which is provided, only to confuse you. What you should know, that the reaction that is taking place inside the fuel cell is giving rise to some energy that is called maximum electrical work, and that energy is used for the compression. Alright, isn't it? So I am taking the work as positive. So you have to equate this value so that you get the delta T. Okay. Now let's see the next question. You can see the question, whenever is asked about a weak base added with a strong acid or something, one has to understand that combination is probably making up a buffer. So likewise here also the combination is making up what? You see, whenever you use a weak base, let's say BOH, is added a strong acid, so you will be getting Ba and water, isn't it? Now you can see at two instances, at pH equal to 11, the pH had almost remained constant, and at pH equal to 1 as well, it had remained almost constant. That means these are acting as the effective buffers. What are they acting as? The effective buffers, right? There are two instances where the buffer will function effectively, right? One is at the half equivalence point. Second is just at the end of the titration, near the end of titration, not almost completion of the titration. So at these two instances, you can say, I'll take any scenario. I'll take this scenario, say I have started with A moles at the half end point. You know that the number of moles of BOH consumed are A/2 and salt produced are also A/2. Now we can see weak base and salt with a strong acid will make a basic buffer, right? You know, for basic buffer, what do you write? POH equal to pKb plus log concentration of salt by concentration of weak base, whose values at the half equivalence point are equal. Now you can see pH at this point is given as 11. So POH will be 14 minus 11, that is equal to 3. Therefore, POH equal to pKb. So right answer for this question, because this is log 1, that is 0, is 3. Question looks to be lengthy, complicated, but there is not much story involved in it. It's an easy question. Now the other one, when I take the whole question paper related to these chapters, I could see this is a relatively easier question. So what's happening here, one must know that SnO2, which is a solid, is getting reduced to the Sn. I can see the data which is provided, and based on that only I am writing here the reactants and product. You can see this is out of your common sense. This is the overall reaction, isn't it? Now what is that you need to find out? You have to use the data to find out. Alright, now we can see that first of all, use the data, minimum reduction of gas trade would take place, right? That means the spontaneity temperature at which this reaction is spontaneous, that means it will take place on its own. Alright, so spontaneity is delta G equal to delta H minus T delta S. Alright, so first let me find out the values of delta H as well as delta S. Alright, so delta H equal to heat of formation of, this is solid, this is solid. For solids we take the heat of formation as 0, for this elements in the standard state we take it as 0. So you have been given the heat of formation of carbon dioxide. How much is that? 394. This is the heat of formation of product minus heat of formation of reactant is also given minus 581. So you got the delta H value. And moving on further, delta S is equal to the entropy of the product minus entropy of the reactant. You can see that the entropy of tin 52 plus entropy of the carbon dioxide is 210 minus entropies are not 0 minus entropy of SNO2 56 plus entropy of carbon which is given as 6. So you have to find the value of delta S, right? So you got delta H as well as delta S. After getting this, you see the minimum temperature, right? So minimum temperature, at least this is spontaneous, that means spontaneity criteria starts from 0, isn't it? Delta G equal to 0, that is delta H equal to T delta S, or temperature which is required to carry out the spontaneous reaction is, so you got delta H and you got delta S. Indeed they are delta H naught and delta S naught. So you have to find out the ratio, right? Substitute these two values and get your answer. This is easier comparatively. So long back there was a question on Mg plus 2 is being precipitated as magnesium hydroxide, and to prevent that we were adding what you call ammonia. This is also somewhat similar to that existing question, wherein the information suggests that you have to solve it in a very precise manner without getting jumbled, because when there is an excess information, when there is H2S and net values are given, we get tempted to write the whole equation like H2S is splitting into H plus HS minus HS. Don't require all that. You can see overall what is happening. You have been given KSP and you have been given the net dissociation constant, and we are talking about the prevention of precipitation of ZNS, where you need to find out the concentration of H plus. That means equilibrium situation only, because from equilibrium only either you can precipitate or not precipitate, isn't it? In the previous case, in the previous question you have seen that is the equilibrium stage from where the reaction tend to become what? Spontaneous. So here also we have to see the case of equilibrium, right? So what I will take is the equilibrium of the ZNS dissolution. I will take the opposite of it. You can see that this is 1 by KSP, that is 1 by 1.25 into 10 to the power 22. I have done the inverse of this, because whenever you are writing the reverse of the equilibrium constant get inverted, isn't it? Now let me take the other equation also, the complete dissociation of H2S. Net value is given, so I will not take the part dissociation like we did in the first question or second question. We will take the complete dissociation, wherein you are given the K net as 1 into 10 power minus 21. Now I will take these two equations. Why am I doing this? Because I have to get to the net equation where there is no extra species which is involved. I have to take Zn plus 2 plus H2S is in equilibrium with ZNS, because this is ultimate equation. This is related to the precipitation of what? The ZNS. So this is where I need to end up. So when I am summing up the equilibrium constant gets multiplied. What is the equilibrium constant here when I am multiplying? Isn't it? When I am multiplying these two, I get this, which is equal to, this is solid, so you need not take its concentration. Concentration of H plus whole square, that is you need to find the concentration of H plus, and you can see the ZNS is given as how much? 0.05, right? The concentration which is supposed to get precipitated, and the amount of H2H which is required to do that so is nothing but 0.1. That's all. You have to get the value of the concentration of H plus which is required to prevent the precipitation of ZNS. That means this is the minimum amount that is required to cause the equilibrium to achieve. More than this will shift the equilibrium to the backward and the precipitation formation is prevented. Alright, so you might be thinking, why do we have to take the direct values here? You can see it is mentioned that it is a saturated solution, isn't it? That means the concentration values are already at equilibrium. Or you can see the what you call the equilibrium constant over here. Unless these are the equilibrium concentration, you could never get these values because these values are very less. You can see that if I take the reverse of this equilibrium, you can see this value is very less. So I can't expect this Zn plus 2 to be 0.05 unless it is given that it is a saturated solution. That is the reason why we could take boldly the concentration of Zn plus 2 as 0.05 and H2S is 0.1 because it is saturated. Saturated means it is equilibrium values. This is the important point one has to catch. So let's see the last question of the day of this session. This is again theoretical. Alright, as we all know that work done on the gas, you can see that the gas expansion is taking place under different conditions. So you have to draw certain conclusions out of it. So this is again the comprehensive revision of the theory. This will help you in revising the theory. You can see that the work done on the gas is maximum when it is compressed irreversibly from P2 V2 to P1 V1. This is a correct statement. Why actually we study the contrast of it? How do we study? We study it like this, work done in reversible expansion is maximum. Therefore, in converse, in opposite to it, we write this statement that work done in irreversible compression is maximum. Ekdam ulta. In reversible expansion is maximum. In irreversible, the opposite, because for reversibility, irreversibility is opposite, right? Irreversibility, you don't have any formula as such to calculate. Alright, so whatever we derive, whatever we study in thermodynamics is actually for reversible changes. And from reversible only you make conclusion for the irreversible thing, isn't it? So if you want to study irreversible, the nature will not support you because all the processes occurring in the cosmos are irreversible. So we cannot practically do that. That is the reason why we have to take the reversible cases and apply the contrast statement to the irreversible process. So in reversible expansion, the work done is maximum for expansion in the reversible process. Therefore, for irreversible process, for compression it is maximum. Remember like this. And moreover, this is for option A. Let's see option B. You have studied, isn't it? For the work done we usually use the Boyle curves. These are the two curves which are related, and one is the reversible isothermal process and this is reversible adiabatic process, and area under the curve is actually the work done. Therefore, it is understood that reversible isothermal expansion work done, reversible isothermal expansion is greater than that of reversible adiabatic expansion. Alright. Okay. So this second statement seems to be okay because you see reversibly under adiabatic is less. Alright. So seems to be okay. Let's see the third case. The change in internal energy of a gas is 0 if it is expanded reversibly, T1 equal to T2. For isothermal process, delta U equal to 0 looks to be the one statement 1 looks to be okay, but this is where they will confuse you. As soon as you see statement 1, you will assume that statement 2 also might be correct. Alright, but you can see that here it is given as adiabatic condition. I am talking about the option C. Check out carefully. Adiabatic means Q equal to or dQ equal to 0. That means expansion case delta U equal to minus W. Therefore, it has to be negative, isn't it? Alright, the change in internal energy is negative, however it is mentioned as positive. So this is a wrong statement. Let's see the next one. If the expansion is carried out freely, right? Free expansion, option D. What do you mean by free expansion? Free expansion means external force applied is 0. P external equal to 0. This implies work equal to 0. Now we are talking about a situation, right? Option D we are talking about, and in option D we are talking about the work done, right? Delta U equal to Q minus, alright, delta U equal to Q minus W, and since W equal to taken as what? 0, all right. So Q equal to W. That means if I take a situation where it is isothermal, that is delta U equal to 0, therefore Q equal to also 0. That means when I am talking about the expansion carried out freely, that means it is isothermal as well as adiabatic, because both the values are pertaining to be same. Is it understood? Hope you have liked the video. Please press the like button, share it and subscribe to the YouTube channel. This channel is purely the chemistry lesson. There is no drama, no nonsense, advanced, mains, NEET, etc. I am KASU sir, here to help you in understanding the concept through the numericals, and we will try to solve these questions in the minimum time. So we have intended here to carry out the 15 sessions, of which 3 sessions are successfully completed. I hope you are liking the content which I am delivering. If you have any suggestions, any comments, please mention in the comment box. Until then, take care. That's it for today.